Hello, it's Keith here, and this is lesson 9 of the Photon series of my Z80 programming tutorials. Photon is my little game. It's a Tron clone here. You can see it just here if I can remember the controls for it. All different versions have different controls. And this is the MSX1 and the Master System version. So basically this becomes a tutorial in pixel plotting on these systems. Now there is a bit of a problem with the Master System version of the game, or sort of a problem because I fixed it, but basically to fill the Master System screen we need a total of 768 tiles, and basically we're just changing the pixel data of one of those tiles to set the colors of that pixel. But the problem is the Master System only has a total of 512 tiles, and that's that's in theory, because actually some of the tiles are used up by the other tile map data, because that would use the limit of the VRAM. So we don't have enough tiles to fill the screen in the Master System screen mode. But we do have a trick. You see, the MSX1 has the ability to use this special mode where each strip of the screen uses a different 256 tiles, allowing for the 768 we need to fill the screen, and that will allow us to make the game have every pixel of the screen different. And actually the Master System has the backward compatibility with this MSX1 mode, and that's what we're using here to make the game work on the Master System. Now interestingly, even though the game gear is almost identical to the Master System, it seems this screen mode doesn't work on that system. I don't know if you need the Master System converter to make that screen mode enable, or if it literally doesn't support it, but it doesn't work on there. But I do have a version of this game for that system, and ironically that game will actually work on the Master System as well. It just can't fill the entire screen because, as I say, there aren't enough tiles. So we will be running on the game gear as well. You can see the version here. And this version will also work on the Master System, but just in a small screen. Slightly bigger screen than the Game Gear, but still a smaller screen. Now, the difference is if we run when using the MSX screen mode, we get that full screen graphic, but the colors are a little bit different. We've got less color options, so it's just a trade-off, and you just need to decide for yourself whether your priority is the better color or the bigger screen. And I think the bigger screen is the more important thing, so that's what I'm using. Now today we're only going to be really focusing on the pixel plotting routines and also the common code. We're not going to look at things like joystick input because we've covered those before in YQuest, and to be honest I'm getting quite bored of it. If you're not quite bored of it, please take a look at YQuest, wherever we've covered all of this in great detail, and also the simple series. I've been over quite a lot. So okay, let's have a look. Now the start of our code is basically all the same on the Master System or the MSX1, and there's just a few slight tweaks depending on the system, but mostly it's the same. So we're going to go over the Master System version, and I'll just raise the slight differences where they occur. So first we're defining some game memory. The game uses about 64 bytes, and we're allocating a position for them. And then we're defining the 4 colors the game is going to use. And these are in MSX1 color attributes. Now if you're not familiar, I will explain. In the mode we're using, the MSX1 compatibility mode, the way it works is there are 2 bytes that relate to each line of a tile. The first byte defines whether each pixel of 8 pixels is using the foreground or the background color, and then there's a matching color attribute byte which defines what foreground and background color those 8 pixels use. So unlike a system like the Spectrum, which uses an 8x8 block, the MSX and the Master System in this mode use an 8x1 strip, and there is a common color for that. So we're defining those colors here, and we're defining the foreground colors here, and in each case the background color is black. We're then defining our screen resolution here, and this sets some of the attributes of the game. We've got a nice big screen. This is kind of an ideal screen. On the Sega Game Gear version, which as I say does work on the Master System, it's a smaller screen because we haven't got enough tiles to do the nice big screen. And then what we're doing here, we've got some stuff here for the start of the cartridge. Now that is different on the MSX1 version, of course. But the first thing, once we've done all that kind of stuff, is we are setting up our screen here, and we're sending the VDP data to set up a screen, and it's identical on both systems here. Basically these are the settings. Now the usual Master System mode is slightly different. This is mode 2 we're using here, and the important bits here for both, and the new bits if you will on the MSX version, are the 2 bits at the bottom, and they are the same on both, and it's these 2 here. And what these are doing is they are defining that the screen is split into 3 strips, and there's 256 different tiles for each of the 3 strips, and that's how we're able to get 768 tiles on the screen. You can't have a tile from the bottom strip in the top part because it uses different tile definitions for all 3. It's just 1 byte per tile, you see. That's the limitation. So that's enabling our screen, and then what we're doing is we're filling the strips from 0 to 255 tile numbers so that every single tile of the screen is different within those strips. So each strip is going from 0 to 255, but because each strip is using a different set of pattern data, they will all have unique pixels. Now this fill tiles routine here is something we've looked at before. The tile map starts at 1800 here, and there's 768 bytes, 1 byte per tile. We're then clearing the user memory here, and we're showing the main menu. Now this is the start of the main game loop. The game works like this. Basically, our game allows us to move our player. If I just start the game here. Now, if I hold down the fire button, I actually move faster, and that's called boost mode. Now, the other thing to note is this: if I press right and I hold right, I don't keep moving right. I have to actually press and release to turn, and that's intentional so that we don't crash into ourselves. So that's something we're going to see in the code here. So here what we're doing is we are checking the tick number, and we're just updating it, and in boost mode we move every tick, and in non-boost mode we move every other tick. Now when boost mode's enabled, we actually update the tick counter, and because my vector font is disappointingly slow, we actually have to change the delay of the boost mode to compensate and make it faster. So that's what we're doing here. And the reason I use the vector font is this entire game is graphically just based on this single pixel routine and the vector routines. So while the bitmap fonts would have been better for speed, for portability, it wasn't ideal. So that's what we're doing there, and then we are testing the joystick. Now, of course, our joystick reading routine is going to be a little bit different depending on the system. So we've got the version here. This is using the read joystick, and on the MSX1 we are actually using a firmware core, whereas on the Master System we're just reading in directly from hardware here. What we're doing next is we're checking if any keys are pressed. If the keys have been released, then we're going to clear that timeout just here. And if not, we're just going to keep looping around. We'll read in any key presses that occur, and we'll process them after the loop here. What we do next is we're checking if the key timeout is cleared. That means the key's been released, and if it has, we're going to process the input. But if not, we're going to skip over it, and we're going to go right down here and just update the player and the CPU. Then we're setting boost to off here. We will reset that if the fire button's pressed. We then set HL to the player's current direction and IX to the current acceleration. We then check left and right, and if the player has pressed a direction, we're going to decrement or increment the player direction and run set player direction, which will update that acceleration accordingly. In each case, if the left or right is pressed, we set the key timeout so that we won't accidentally turn around again before the key is released. Now, if the fire button is pressed, what we're doing here is we are checking if any boost power is left, and if it is, we're zeroing boost, and that will accelerate the player. All of that is actually done by the handle player routine there that draws and handles the player. That's been covered in the multi-platform episode of this series. And then handle CPU does the CPU AI and all that good stuff. And then we just loop all the way back up here. Now this is common code basically. It's almost identical on the MSX except for that fire button routine here. The read joystick routine you can see just here. It's just very slightly different here, just depending on the system how we do that. But that's not what we really want to focus on today. It's this PSET and this point routine, the PSET being plotting a pixel and point being reading one. So we pass BC as an XY coordinate and D as the color number. Now each byte of the screen contains 8 pixels, and so we're going to need to work out from the bottom 3 bits of the X position which pixel we want to change, and we've got a lookup table here to do that for us. So these are the masks for the pixel we want to change. So we're going to read in one of those according to the bottom 3 bits of B, which is our X position. We read in from that D, which is the mask for the bit we want to change. We then flip the bits and store that in E, and that's the mask for the bits we want to keep, because we don't want to change any other pixels in the same byte. Then what we're doing is we're calculating the memory address from the XY position. Now each tile is stored consecutively in memory, and the 8 bytes for the 8 lines are consecutive. The color information is further in VRAM. So what we're doing here is we're taking the Y position here, shifting it to the right by 3 bits. The bottom byte is then the X position, but less the bottom 3 bits, and we then OR in the 3 bits here from the bottom of the Y position, because the memory addresses effectively go down the tile, then jump to the next tile, down the tile, all the way across the line, and then start at the next line. So this is calculating the address of the line within the tile of the pixel that we want to change. And of course we know the mask for the pixel based on this. So next what we want to do is we want to read in any current data in that position. So we've got this function set read address just here, and this is identical on the MSX1. It's absolutely identical, which is why we're covering both of these today. So to set a read address, we just send the HL address to the VDP control port here, and that will select it for reading. So we've selected it for reading. We read in the current state of the byte. We then mask it with C, which we backed up there and popped back into BC here, and that will remove the 1 pixel we're planning on changing but keep the others the same. We're then going to check the color we want to set, and if it's 0, we're going to basically do nothing. We've got that pixel set to 0 now, so we're going to write it back to the screen. But if it's not 0, we're going to want to OR the bit from that mask in to set the pixel to bright, and that's what we're going to do just here. We're doing that here, and then either way we're writing back to the screen here. And then once we've done that, what we're going to do is we're going to set the color attribute for that block, because the color attributes are set for an 8 times 1 pixel block. Now the addresses for the color attributes are quite conveniently starting from memory address 2000 in VRAM. So all we do is we OR in hexadecimal 20 to the H part, and then we use set write address. We've looked at this before, almost identical to set read address. We just set bit 6 of the H part, and that will define it as a writing port. And so we do that, and then, where is it? And then we transfer our data to the VDP port just here. That's how we are setting a pixel. Now, reading a pixel is almost the same. I mean, effectively, we did it here. It's just a slight tweak to how we deal with the data we read in. Instead of ANDing with C, which was selecting the bits we wanted to keep, this time we're ANDing with B, which is the 1 pixel we're interested in. That's selecting the pixel, and if that is a 0, then we are returning 0. Otherwise, we're returning 1. Now, we're not checking the color attributes in this case. I mean, we could, I suppose, but it's not relevant for this case. We just care if it's black or not black for the logic of the game, and that's how we're doing things. So that's how we are plotting and setting pixels. Now, when it comes to clearing the screen here, all we're doing is we're zeroing all of that data in one giant copy here. We've got an alternate version of the PSET routine here, which protects all the registers, just in case we need to do that. Sometimes it's easier to work with D and HL for line drawing and A for the color, but by default, it's using B, C, and D. And that's how we're plotting the pixels to the screen. And I think this is a quite ironically useful way of doing things for the Sega Master System, considering in this case the limited tiles. It's not usually limited on the Master System, but in this case for pixel plotting, I think this is worth considering. But if you don't like it, please stick around for next time and the Game Gear version, where we're going to run that Game Gear version, which does use the 16 color mode instead, and it does work on the Master System just with smaller tile area. So there we go. Anyway, if you've liked this, please like and subscribe. That all helps me out. And of course, you can go to my website and download the source code and play with it to your heart's content and have fun plotting pixels on the MSX1 and Sega Master System. Anyway, thanks for watching. If you've liked what you've seen today, please consider backing me on Patreon. Every video I make takes about 5 to 10 hours of development, research and documentation for the website, so it really takes a lot of time, and it's only through the continued backing of my patrons I'm able to keep justifying putting the time in, to be honest. So if you are interested, you can support me on there. I release my videos to the Patreon backers way before regular YouTube viewers, and also when questions come, I always prioritize the Patreon backers when it comes to requests and suggestions and things. Although of course all my videos do come out to non-Patreon backers eventually, because I do consider them to be an educational content that really everyone should have access to. But as I say, if you want to support me, you can do so on Patreon. Links in the description below. Also, I now have a Teespring store, so if you want to buy some Chibi Akumas or learn ASM merchandise, you can go ahead and find something on there, and I'll probably be releasing some new designs if people seem interested in it. Anyway, whatever you do, thanks for watching today, and goodbye.